back for another exam review video. Today we are going to look at complex numbers and also coincidentally review the binomial theorem, which isn't really related to complex numbers, but I'll show you how I think it relates a little bit too. So anyway, before we dive into some actual problems, just a little bit about complex numbers. So a complex number is a mixture of a real part and an imaginary part, something like 3 minus 4i. And you can graph a complex number using kind of like an xy plane, but it's a real plane and an imaginary plane. And so the number 3 minus 4i would be 3 steps in the real axis and 4 steps down on the imaginary axis, and could be represented by a point like this. And the real power in complex numbers is that by adding or subtracting or multiplying complex numbers, you can describe motion. Adding complex numbers, which is super easy to do. You simply combine the real parts and the imaginary parts, just like they were variables, combining like terms sort of thing. That describes motion, just moving, translating, and multiplying. I can't quite read all that, but multiplying describes a combination of both rotating and scaling, making something bigger. And so if you were to multiply either a point or a number or an image by 3 minus 4i, what it would do is it would rotate it a little bit. This is just 1. 1 times 3 minus 4i would rotate it this about 50, 60 degrees or so, and it would stretch it by a factor of, I don't know, 4, 5, 6-ish, somewhere in there. And so that's what multiplying complex numbers is good for. Unfortunately, in high school level math, you don't really get enough time, I don't think, to get into a whole lot of those applications. But anyway, to multiply complex numbers, you simply multiply by like foiling. You multiply with this additional constraint that if you ever get an I squared in a problem, I squared is turned into -1. And so that's the idea behind multiplying. Now, complex numbers can be written in what we call a plus bi form, which is what we have here. We've got the real part and the imaginary part. But you can also write it in what is called polar form. And so polar form, here are a couple different examples of that. Polar form emphasizes that multiplication aspect of a complex number, where in this case the number in front, I think it might be called the modulus. I'm not really sure, but this number in front is the absolute value of 3 minus 4i. It's the length of 3 minus 4i, and you find it using the Pythagorean theorem. A squared plus b squared equals, it's traditionally called r squared. And so in this case, 3 squared plus 4 squared is 9 plus 16 is 25. You take its square root and you get 5. And if you multiply something by 3 minus 4i, not only is it going to rotate, but it's going to get 5 times longer. That's what this 5 is all about. How much it rotates, remember when I looked at this picture, I said that that was about 50 or so degrees down. You can find that angle exactly by using the inverse tangent of the slope. So the inverse tangent of -4, the height, over 3. You type that into a calculator, it's about -53 degrees, and so it rotates it 53 degrees. You can write it a handful of different ways. This is a really sloppy way that's never in any textbooks or anything, but just kind of emphasizing those numbers. This is a more common technique where you write it as 5 cosine of -53 plus 5 sine of -53. Again, cosines are like the widths and sines are like the heights. And so that, I think that kind of makes sense. The height in this case is an imaginary part. That's why there's this I. And then there's a very odd looking way of writing this as well, and that uses E and I as an exponent like this. And though it seems kind of strange to do so, there is good reason to do that. Unfortunately, with this coronavirus, we kind of ran out of time before I could fully explain why e to the I notation makes sense, but it does. And I hope you'll have a chance to learn that again in calculus next year or something like that. But, whoa, we got big here. There we go. Anyway, those are another format. And again, those are useful if you're going to be doing a lot of multiplications or exponents, powers, dividing, so forth. You want to write it that way. Now, what are the sorts of questions that I want you to demonstrate for me? And so I'm going to ask you to demonstrate the same problem, finding it two different ways. And so here is an example problem. Spoiler there. Now you can't see it. What is 3 minus 4i raised to the 6th? And so we could answer that question a lot of times. If you just want to answer immediately and you don't want to think about it, you can type it into your calculator and you'll get an answer, some giant combination of real and imaginary numbers. And that's fine. But I want to understand how to find this answer. And one way that I want you to show me is to use de Moivre's theorem. And de Moivre's theorem involves you putting this in the real, or in the, what was the name of it? Exponential form, the polar form, excuse me, putting in polar form, and then using the, well, why don't I just, well, as we get there. So if we put this in real, in polar form, we found that earlier that 5 was the absolute value and the angle was negative 53. And so here is polar form of that same problem. 5 e to the negative 53i raised to the 6th. And the benefit of writing it in this format is now exponent rules apply. So the 6 is an exponent outside of the group, can be applied to the 5 and be multiplied by the negative 53. And so that's this step, 5 to the 6th, and e to the whatever 53 times 6 is. And so now 5 to the 6th, got to use a calculator on that one, it's a little big for me. That is 15,625. And when I multiply these, I get negative 318. There should still be an I there. And now, how do I get some sort of a number like this back? 3 minus 4i, or something plus or minus something I. And to do that, I will translate this into the other type of polar form, which is using cosines and sines. So here is the still the distance, and then putting it in cosine plus I sine form. And I can now just type this in my calculator. 15,625 times the cosine of negative 318 degrees, and 15,625 times the sine of negative 318 degrees. If I type those in, I get these numbers. And these numbers aren't exactly right because I rounded and so forth. Most likely this is probably 53 rounded up, and this is probably just 10,1296. Oops. So we can figure out what the real answer is a second by simply typing it into my calculator. 3 minus 4i, and raising it to the 6th power gives us 11,753 plus 10,296i, which is pretty close to what we had here. Again, it wasn't exact because I had to round along the way. Now, what's probably a bit surprising is this process is what, oops, this process is what your calculator did when it got the answer. So behind the scenes, it converted it into polar form. It did some multiplications like this, and then it converted it back. And because it was able to keep track of more digits than we were when we did it by hand, it was able to come up with this answer exactly. But every once in a while, your calculator gets off. And you've seen that, I think, when we do something like I to the 17th, and it gives you this something plus 0.000000I. That is your calculator showing that it's not perfect. And so, anyway, that's something I wanted you to be aware of. Every time you use technology, it's not always necessarily perfect. It's certainly been designed and sometimes has approximation errors. So, anyhow, how could we do this problem a different way? So that's the other thing I want you to show me. I want you to show me how you can find this another way, which is an important theme for this year, that there are often multiple ways to do something, and they ought to be consistent. And if they're not, something's wrong somewhere. So one way we could do this, 3 minus 4i to the 6th, well, that just means 3 minus 4i times 3 minus 4i times 3 minus 4i, and so forth. We could FOIL and FOIL and FOIL and multiply, and it would take a long time, but it's doable. I'm not going to recommend you do that because that, like I said, is going to take a long time. For problems like this, where you are taking two terms and raising it to a power, there's a shortcut, and that shortcut is called the binomial theorem. And the binomial theorem, remember, involved a combination of some numbers from Pascal's triangle, and then this first chunk raised to various powers, and the second chunk raised to various powers. And so in this case, this is a raised to the 6th. So if I get out Pascal's triangle, the 6th row here, I need those numbers, 1, 6, 15, 20, 15, 6, and 1. And so let me write those down. And then each one of these numbers is part of one of the terms in this expansion. Now I need this first chunk raised to various powers. And so in the first term, it'll be 3 to the 6th, and then 3 to the 5th, and 3 to the 4th, and so on all the way down. And so these numbers are necessary. Notice you'll run out of a term, and so there won't be a term for that last. There won't be one of these factors in this last term. Then you follow that up with minus 4i raised to various powers. So this is going to have minus 4i to the 6th. This will have minus 4i to the 5th, and to the 4th, and to the 3rd, and so forth. And so that will look like this. Now, I forgot the negatives, so let me include a negative here, and a negative here, and a negative here, and so on. Sorry, I promised myself I would do these videos in only one take, so you're going to have to bear with me. I'm not going to redo this. So now, each one of these terms then needs to be multiplied out. And so over here, 1 times 3 times 3, 1 times 3 to the 6th, that is 729. 6 times 3 times 3 times 3 times 3 times 3 times negative 4i is this, although I have it wrong because I forgot the negative. So this would have to be negative 5,832i. If I multiply all these out, you should get negative, or 19,440. This one will be a positive term because there are two negative signs. This term here, there are 3 negative signs, so that one comes out negative. This term here, there are 4 negative signs, and so that one should be positive. This one here, there are 5 negative signs, so that should be a negative. And then this last term, there are an even number of negative signs again, so that should be positive. And so this is pretty good, except for there's a little bit more cleaning up that we can do. Remember, I squared is the same thing as negative 1, and so I can replace I squared with negative 1. And I cubed is the same thing as negative I. And so a negative I times a negative 1 that's in the beginning means that this is a positive imaginary term. I to the 4th, remember, is just 1. And so 34,560 times 1 is 34,560. This negative, this I to the 5th is the same thing as I. And so this is a negative imaginary term. And I to the 6th is the same thing as I squared, which is the same thing as negative 1. And so this term is negative real part. And so now I've got a mixture of i's and non-i's, real and imaginary parts. And so if we combine all the real parts together, that's just a number. And if I combine all the imaginary parts together, that also is an imaginary number. And so we've got a little bit of adding to do. 729 minus 19,440 plus 34,560 minus 4,096 gives me 11,753. And if I add those imaginary parts together, negative 5832 and 34,560 minus 18,432, I get 10,296. And that should be what we got when we did that problem earlier. Oops, let me type it again. 3 minus 4i raised to the 6th. Yep, 11,753 plus 10,296i. And so that's kind of cool. I love how multiple ways of looking at this problem are consistent in giving us the same answer. So this is actually a exam question I have given every year for the past 5 or 6 years now, asking students to do the exact same problem, once with the binomial theorem and once with the Moivre's theorem. And so I think you guys can do a similar sort of thing this year. Change the numbers a little bit. Don't do the exact same problem. I wouldn't suggest doing an exponent much bigger than this, just because it will be really tedious. So I think in most of the exams in the past, I've usually done something to the 4th, so that's not too much work to do by hand. So anyhow, that is a little bit of review. I'll have another video ready for you probably tomorrow. Have a great one.